Complete explanation of PNP transistor. A PNP transistor is a type of bipolar junction transistor, BJT. BJTs are electronic devices used in various electronic circuits for amplification, switching, and signal processing. The PNP transistor is one of the two common types of BJTs, the other is the NPN transistor. The term PNP stands for the three layers within the transistor's structure. P-type material, also known as P-type semiconductor, is a type of semiconductor material that contains an excess of positively charged charge carriers, called holes. Holes are essentially vacancies in the crystal lattice structure where an electron would normally be found. In P-type materials, these holes act as mobile charge carriers and contribute to the electrical conductivity of the material. Here's how P-type materials are created and their characteristics. Doping. P-type materials are typically created by adding specific types of dopant atoms to intrinsic, undoped, semiconductor material. Common dopant atoms used for P-type doping include elements from group 3 of the periodic table, such as boron B, aluminum Al, or gallium Ga. These elements have fewer electrons in their outermost energy level than the intrinsic semiconductor material, usually silicon or germanium. When they are introduced into the crystal lattice of the semiconductor material, they create holes in the electron structure. Hole mobility. In P-type materials, the majority charge carriers are these positively charged holes. When an electric field is applied, the holes move toward the negatively charged side, which is typically the cathode or the collector in a semiconductor device. Conduction. P-type materials have relatively low electron concentrations compared to intrinsic or N-type materials, but they have a higher concentration of holes. This means that P-type materials conduct electricity primarily through the movement of holes, resulting in a net positive charge flow. Electron-hole pairs. When an electron from a neighboring atom moves into a hole, it leaves behind another hole. This process can create electron-hole pairs, which can contribute to the material's electrical behavior. P-type materials are essential components in the construction of bipolar junction transistors, BJTs, P-channel metal oxide semiconductor field effect transistors, PMOSFETs, and other semiconductor devices. They play a crucial role in electronic circuits by allowing the controlled flow of electrical current, enabling the operation of various electronic components and amplification of signals. In electronic devices like BJTs, P-type regions are often used for the base region, as they facilitate the control of current flow between the emitter and collector terminals through the injection and movement of holes in response to a base current or voltage. N-type material. N-type material, also known as N-type semiconductor, is a type of semiconductor material that contains an excess of negatively charged charge carriers, which are electrons. In N-type materials, electrons are the majority charge carriers responsible for electrical conductivity, and they move through the material in response to an applied electric field. Here are the key characteristics and properties of N-type material. Doping. N-type materials are created by adding specific types of dopant atoms to intrinsic, undoped, semiconductor material. Common dopant atoms used for N-type doping include elements from group V of the periodic table, such as phosphorus P, arsenic As, or antimony Sb. These elements have more electrons in their outermost energy level than the intrinsic semiconductor material, usually silicon or germanium. When they are introduced into the crystal lattice of the semiconductor material, they create additional free electrons. Electron mobility. In N-type materials, the majority charge carriers are electrons, which are negatively charged. When an electric field is applied across the material, these free electrons move toward the positively charged side, typically the anode or the emitter in semiconductor devices. Conduction. N-type materials have a relatively high electron concentration compared to intrinsic or P-type materials. As a result, N-type materials conduct electricity primarily through the movement of free electrons, leading to a net negative charge flow. Generation of electron-hole pairs. Electrons in N-type materials can move into vacant energy states, creating electron-hole pairs. These pairs consist of a free electron and a hole, an electron vacancy. The generation of electron-hole pairs can occur when the material is exposed to photons, light, or other energy sources. N-type materials are fundamental components in the construction of various semiconductor devices, including NPN bipolar junction transistors. BJTs. N-type regions are often used for the collector and emitter regions in NPN transistors, allowing the controlled flow of current between the emitter and collector terminals through the movement of electrons in response to a base current or voltage. N-channel metal oxide semiconductor field effect transistors, NMOSFETs and NMOSFETs. N-type materials are used to form the source and drain regions, enabling the control of current flow between these regions through the modulation of the electron concentration in the channel region. Photodetectors. N-type materials are used in photodetectors to take advantage of the generation of electron-hole pairs when exposed to light, allowing the conversion of optical signals into electrical signals. Overall, N-type materials are crucial for various semiconductor applications, as they facilitate the controlled manipulation of electron flow in electronic circuits and devices. The emitter, often denoted as E, is one of the three terminals of a bipolar junction transistor, BJT, which is a type of electronic component used for amplification and switching of electrical signals. The emitter plays a crucial role in the operation of a BJT. Here are the key characteristics and functions of the emitter terminal in a BJT. Current emission. As the name suggests, the emitter is the terminal from which the majority charge carriers, either electrons in NPN transistors or holes in PNP transistors, are emitted or released into the transistor's internal structure. Majority carrier emission. In an NPN transistor, the emitter emits electrons into the transistor's base region. In a PNP transistor, the emitter emits holes into the base region. This flow of majority charge carriers is responsible for the transistor's amplification and switching capabilities. Input terminal. The emitter is typically considered the input terminal of the transistor. The base current, for NPN, or base voltage, for PNP, applied to the base terminal controls the flow of current from the emitter to the collector. Small changes in the base current or voltage can result in significant changes in the emitter to collector current, making the transistor an amplification device. Emission control. By varying the current or voltage applied to the base terminal, you can control the number of majority charge carriers, electrons or holes, emitted from the emitter into the transistor's base region. This control allows you to modulate or amplify the current flowing from the emitter to the collector, which is often used for signal amplification purposes. In NPN transistors, the emitter is typically the terminal where electrons are emitted into the transistor's structure, and current flows from the emitter to the collector. In PNP transistors, the emitter is the terminal from which holes are emitted, and current flows from the collector to the emitter. The emitter current is an essential parameter in transistor operation, and it is typically denoted as IE for NPN transistors, or IC for PNP transistors, representing the emitter current or collector current, respectively. The emitter current is a key factor in determining the gain or amplification of the transistor. In summary, the emitter terminal in a BJT serves as the source of majority charge carriers, electrons or holes, and is the input terminal that controls the transistor's output current, making it a fundamental part of transistor amplification and switching circuits. Base, B. The base, often denoted as B, is one of the three terminals of a bipolar junction transistor, BJT. BJTs are electronic devices used for amplification and switching of electrical signals. The base plays a critical role in the operation of a BJT. Here are the key characteristics and functions of the base terminal in a BJT. Control terminal. The base terminal serves as the control or input terminal of the transistor. The flow of current from the emitter to the collector, for NPN transistors, or from the collector to the emitter, for PNP transistors, is controlled by the current or voltage applied to the base terminal. Base current, IB. In an NPN transistor, the base current, IB, is the current flowing into the base terminal. In a PNP transistor, it is the current flowing out of the base terminal. The base current controls the operation of the transistor. Amplification. The primary function of the base terminal is to control the flow of charge carriers, either electrons in NPN transistors or holes in PNP transistors, between the emitter and collector terminals. Small variations in the base current or voltage result in larger variations in the emitter-to-collector current, IEC or IC, making the transistor an amplification device. This is known as current amplification or current gain, denoted as beta for BJTs. Switching. By applying a suitable current or voltage to the base terminal, you can switch the transistor between its on and OFF states. When the base current is sufficient, above a certain threshold, the transistor turns on, allowing a significant current to flow between the emitter and collector. When the base current is below this threshold, the transistor remains OFF, and only a minimal leakage current flows. Input signal control. In many electronic circuits, the base terminal receives an input signal, either current or voltage, that carries the information to be amplified or controlled. Modulating the input signal at the base terminal results in corresponding changes in the output current through the transistor. Base emitter junction. The base terminal forms a junction with the emitter terminal, known as the base emitter junction. This junction is usually forward biased when the transistor is in the on state, allowing charge carriers, electrons or holes, to flow from the emitter to the collector. In summary, the base terminal in a BJT is the control input that determines the behavior of the transistor. By manipulating the base current or voltage, you can control the current flow between the other two terminals, emitter and collector, enabling the transistor to amplify signals or act as a switch in electronic circuits. Collector, C. The collector, often denoted as C, is one of the three terminals of a bipolar junction transistor, BJT, a type of electronic device used for amplification and switching of electrical signals. The collector plays a crucial role in the operation of a BJT. Here are the key characteristics and functions of the collector terminal in a BJT. Current collection. The primary function of the collector terminal is to collect the majority charge carriers, either electrons in NPN transistors or holes in PNP transistors, that flow through the transistor. These charge carriers move from the emitter to the collector, for NPN, or from the collector to the emitter, for PNP. Output terminal. The collector terminal is considered the output terminal of the transistor. The current flowing from the collector is the output current of the transistor, often denoted as IC, for NPN transistors, or IE, for PNP transistors, representing the collector current or emitter current, respectively. Current amplification. The collector current, IC, is controlled by the current or voltage applied to the base terminal. Small variations in the base current, IB, result in larger variations in the collector current, IC, making the transistor an amplification device. This is known as current amplification or current gain and is denoted as beta for BJTs. Power dissipation. The collector terminal is designed to handle higher power levels compared to the base and emitter terminals. It is often connected to a power supply or load in electronic circuits. The transistor's ability to handle power is important for its use in various applications. Voltage separation. The collector voltage, VC, is typically higher than the emitter voltage, V, in an NPN transistor and lower than the emitter voltage in a PNP transistor. This voltage separation allows the transistor to switch and amplify signals effectively. Collector-base junction. The collector terminal forms a junction with the base terminal, known as the collector-base junction. This junction is usually reverse biased when the transistor is in the on state, preventing the flow of charge carriers from the collector to the base. This reverse biasing is essential for the transistor's operation. Heat sink connection. In high power or high current applications, the collector terminal is often connected to a heat sink to dissipate heat generated by the transistor during operation. Proper heat management is crucial to ensure the transistor's reliability. In summary, the collector terminal in a BJT is the output terminal that collects the majority charge carriers flowing through the transistor. It plays a vital role in current amplification, signal switching, and power handling in electronic circuits. The collector current is controlled by the base current, allowing the transistor to serve as an amplification device or a switch in various electronic applications. The operation of a PNP transistor is based on the control of current between the emitter and the collector by a smaller current applied to the base terminal. When a positive voltage is applied to the base terminal with respect to the emitter, it allows holes to flow from the emitter to the base. This, in turn, allows a larger current to flow from the emitter to the collector, creating an amplification effect. In summary, PNP transistors are used in electronic circuits for tasks such as amplification and switching. They work by controlling the flow of current between the emitter and collector terminals using a smaller current applied to the base terminal.